Assalamu alaikum friends. In the previous video we understood the concept of kanade method and how does it helps out in doing tracking. If you want to understand about the concept, then you can follow my previous video in which I explained what is alignment, how do we apply kanade tomasi algorithm to do tracking. In this video I'm going to solve an example to make the concept clear. So if you talk about KL transform or kanade transform, then this helps out to do image transformation by motion. When there is motion, when there is a video in which some object is moving, then your image transforms. So how much is this transformation? That transformation we want to find out. So if I write it down in the form of an equation, the equation of the kanade says that y is equals to a multiplied with x minus mu x. This a is actually the transformation matrix which shows that how much the image has been transformed by motion. So we are going to find out this a. This shows the transformation. So okay, take an image 4 by 4 size. In this image you can see some zeros and some ones. These ones are actually representing where some object is lying. For example, this is a scenery and here there is a flower, there is a car, there is a house, there is some other person standing. So basically I have represented an image in the form of these zeros and ones. So if you mark the coordinates to this image on x-axis and you mark coordinates to this image on y-axis, then we can first of all form a vector of the object in the image. So we can form vectors, motion vectors. You know that in kanade algorithm, if I a little bit refer you to the actual algorithm, that how does it work. First of all, you know that you have to, in simple kanade algorithm, you have to detect the Harris corners. Right now we do not need to detect the Harris corners because I have already told you that these are the objects. So you can imagine that I have placed some Harris corners on all of these images, objects. So these are already my Harris corners. So the second step in this simple Harris corner algorithm says that for each object or for each Harris corner, you have to compute the motion vectors, the translation or affine motions between consecutive frames. So right now what I'm going to do, I'm going to compute these motion vectors. So you can say that for you have to form a vector of the objects in the image. So for 0 1 is basically, this is 0 1, so this is the motion vector of this object. 0 2, 0 and 2, so basically this is the motion vector of this image, which has an x coordinate equal to 0 and a y coordinate equal to 2. Similarly, for this object I will have x coordinate as 1 and y coordinate also as 1. So this is the motion vector of this object. And for this next object, the x coordinate is 2 and the y coordinate is 1. So basically these are my motion vectors which Harris corner wants me to find out or compute for each object. So I have computed motion vectors for all of the objects which are present in the image. All right, and so I have got the motion vectors. Now what does Harris this algorithm wants? This algorithm wants that once you have computed the motion vectors, then you need to link the motion vectors in the successive frames to get the tracks for each Harris points. So of course in the video you know that you have consecutive frames. So now if you have computed the vectors for that object in all of these frames, now you have to link those vectors. If you link those vectors, only then you can know about the tracks, or in other words you can know about the transformation. Okay, in order to link the tracks, first of all what we need is, let's refer back to this equation. We need to subtract the mean from the point For example, if this is the point 20, then I know that I have to subtract the mean from it so that I can get this translation, and that can be multiplied with my transformation vector. So I will find out the mean of the vector. In order to find out the mean, you have two components of the mean, x component and then we will have the y component. So for x component you add 0, 0, 1 and 2 divided by 4, and for y component you do 1, 2, 1 and 1 divided by 4. So I got 0.75 and 1.25. This is my mean for the vector x. Alright. In third step, we are going to find covariance matrix. What is this covariance matrix? Basically, covariance is actually your error. All of your data points minus your mean and multiplied with your data point minus your mean transpose. So this is how you find out actually the covariance. So for your first data point, you have 0 and 1. You can see again that the first data point was 0 and 1. So I will simply subtract the mean from 0 and 1, and the answer is 0.75 and 0.25, and here I have simply taken its transpose. So I'm multiplying this vector with its transpose, and the value that I'm getting, this multiplied with this, and this then this multiplied with this. So first column, first row is this answer, and then first and then second row with first column, and then second row with second column. So I am getting a, since you can see that this is a 2 rows and 1 column matrix, and this is a single row and 2 column matrix, so these points matching with one another say that they are multipliable, and the answer should be this and this, so it has to be a 2 by 2 matrix. Similarly, for the second data point, 0 minus 0.5, because the second data point is you can see that the second data point is 0 and 2, so 0 and 2 and minus mean values, so I'm getting 0.75 and 0.75, and they are multiplied with their transpose, and this is the answer 0.56, 0.56 and minus 0.56 and 0.56. Similarly, for the third data point, 1 minus 0.5, this 1 and 1 are actually referring to this point, so this 1 and 1, and then I'm getting these answers, and I'm multiplying with their transpose, and I'm getting the third covariance variance matrices. So this is how we are actually calculating the error. So now this is the fourth covariance matrix, in which this is the fourth data point, and these are the mean values, and these are the answers, and this is the transpose. So once we get all the covariance matrices, then we find out the mean of these covariance matrices. How do we calculate mean? Actually, we want A, B, C, D values. So for finding out A, we add this first value of all the covariance matrices and divide it by 4. For calculating B, we add this value of all the covariance matrices and divide it by 4. Similarly, for C and D, we add all of these values of all the covariance matrices and divide them by 4. Alright, and in this way we find a mean error, a mean covariance. So basically we have finded out the error. You know, in the Lucas algorithm, we actually need the error. I taught you in my previous video that we have to find out the error, and you can refer back to this video from the link, and just for your explanation, a little understanding, I will explain that when we have an image, then we actually find out the error of that image by subtracting it from the template. So right now we do not have any template, but we are finding out this error. So error is actually calculated with the help of this covariance. Okay, so once we are done with the error, in the next step of the kanade tomasi tracking is, that if you follow the steps, you are finding out the alignment, you are trying to find out this motion vector. So if you want to find out this motion vector, what you want is, you want eigenvalues and you want eigen vectors. With the help of these eigenvalues and eigenvectors, which you are going to find out for this covariance matrix, we will actually find out the transformation. So you to find the eigenvalue, simply subtract this minus lambda from this first value and minus lambda from this fourth value. And we know that the covariance matrix is a symmetric matrix, so it can be written as this term is multiplied with this minus this term multiplied with this is equals to 0. This means that we are saying that determinant of this matrix is equal to 0. So when it is 0, then I can take this second term over to this place, and when we do this multiplication, we will find an equation in lambda square 0.875 lambda and 0.095. And from there, by applying the quadratic equation solution method, we get two values of lambda. Lambda 1 is 0.125 and lambda 2 is 0.75. So these are my eigen values. So till now we have calculated the eigen values. In the step 5, we have to find out the eigenvector. These eigen values which we find out previously, they help us to find the eigenvectors. So eigenvector for the first eigenvalue 0.125 will be calculated by simply placing the value of 0.125 in the place of lambda on both these positions and multiplying this vector with x1 and x2, and on the right hand side it has to be 0. It is just like that. Over there we also placed 0, there was no x and y, that was the only difference. So when we multiply this vector with x1 and x2, first row with first column, and similarly second row with first column, then we will get these two values, and from here we can get the value of x1. So if we put x2 equal to 1, which you can see over there, then x1 is equal to 0.33. so this is my eigen vector for lambda 1. So here we have find out first eigen vector. We already had this eigenvalue, so for this eigenvalue we have find out the eigenvector. Similarly, we can find out the eigenvector for the second eigenvalue. So we place the value of lambda 2 over there and over there, and we multiply it with x1 and x2, and if we do that, then we get this equation, and from this equation we can find out the value of x1. If x2 is kept as 1, then we get the value of x2. So this is my second eigenvector. So now from the transformation matrix A, write eigenvector corresponding to largest eigenvalue first. So you always know that your transformation matrix is such that your eigenvectors come into that transformation matrix, and first of all you get the vector for the largest eigenvalue. So we know that your eigenvalue lambda 2 was large. What was that? If I again recall, first eigenvalue was 1 was 0.75. so basically this eigenvalue was 0.75, and this second eigenvalue was 0.125. So because this eigenvalue was large, so I placed the eigenvector with the help of this eigenvalue on first position, and this was the second eigenvalue, so I placed its eigenvector on the first position, and the eigenvector of the small eigenvalue is placed on the second position. So x is the expression which was given to us in B, and mu is the expression we find out in C. So if we substitute a value into this y, then we will get the output image transformation. So you can see that basically our aim was to find out the transformation matrix A. So we have actually find out, we can make this equation, and you see that we have already found out this matrix A. So this is my transformation matrix. So this is what is actually the Lucas-Kanade transform says, that we have to find out this transformation. Once we are found with this transformation, then you can refer back to this overall scheme of this Lucas-Kanade, that you have actually find out this delta P, because with the help of error which you found in with the help of Lucas, with the help of you find out error in the form of covariance matrix, and you actually multiplied that error with your you find out your eigenvalues and vectors with the error. So this is what you are getting with the Lucas-Kanade algorithm. Thank you very much, and I hope you like the solution. So do subscribe it. Allah Hafiz.